This week's going to be about temperatures. So we're going to look at heat versus temperature. Heat is the total kinetic energy of the atoms or the molecules that compose a substance. If you're looking at temperature, temperature is the average kinetic energy of those individual molecules. Now, you have to have some kind of median in order to measure temperature, whether that's skin touch, air, that kind of thing. If you go out into space, like actual space, there is no temperature because there's no median in order for you to measure those average kinetic energy of any type of molecule. Now, you do hear that they say that there's temperature in space, and you'll hear them talk about it, but how they end up doing that is based off of stuff that it has touched. So you're trying to measure what the outside of the International Space Station is. If it's facing the sun, then its temperature will be hotter. If it's not facing the sun, then the temperature is extremely cold. So you're getting that measurement based off of a metal, so you have that median in order to do it. Of course, here on Earth we have the atmosphere itself, so we have air and we can measure temperature. Now you can look at temperature many different ways. Just the plain old number, what's the temperature outside. Or you can start doing some averages. You can get the daily mean temperature, you can get the daily temperature range, monthly mean temp, annual mean temp. Those things are more useful for plotting data to get an overall picture of what it might be like at an area, basically climatology type of information. It's not something you want to use on an everyday basis. And the same thing with just finding the average temperature for that day, where it's take 30 years of data and they determine what temperature we should be for this time of the year. Again, not great ways to look at it as an individual number, but getting an overall trend, then yes, it's very helpful. Here's an example of a daily mean temperature, and this is for Colorado Springs. And you can see January through December what the annual or the monthly mean for that month is for the temperature. And you can see what it's like. So in January, they're typically 28 degrees Fahrenheit for their overall for their month of January. Obviously, each day can be much different. It can be above, it can be below. Of course, that's how you get your number. And then when you get to July, their summertime, then they're closer to 70 degrees. Again, not every single day 70. You'd have ones that are 80, 90, and ones that might be 60. Again, it's just an average. So it's a way to look at it, just to give you an idea. Hey, I want to move to Colorado Springs. Roughly, what's it like? Boom, here you can look at it and you can get an idea if that's the kind of temperature range you'd want to live in. Now when you're looking at weather maps, most of the time you see isobars, the lines of constant pressure, but you can get maps that do isotherms, lines of constant temperature. In this case, this is one from the UNISA site, and it uses color coding. So you're not really seeing the lines. The actual white lines you're seeing are the pressure lines. So in this case, along here is, you look at the key down below and you can see what temperature that is. And the ones that we'll be using a little bit easier to look at would be the AMS maps. And you can see that it shows in red the isotherms. So you can see all along this line right here, that's 70 degrees. So between the 70 line and down here's the 80 line, so everything in between here is somewhere between 70 and 80 degrees. And that gives you a nice idea of what things are roughly like. Now this is a picture taken at 15Z this morning, September 28th, when that strong cold front was approaching the Kansas City area. So you can see the isotherms on this side in the 70s, the isotherms on the other side in the 50s and in the 60s. It's a very strong cold front that's moving through, and we'll look at that in just a little bit. Some temperature facts. Again, temperature is a measure of a degree of hotness or coldness of a substance, and you need some type of median, as we were discussing earlier. One of the primary climate variables that is measured is actually temperature. You can look at it in several different units: Fahrenheit, Celsius, or Kelvin. Fahrenheit and Celsius are going to be the ones that make more sense to use. Kelvin is more useful for numbers that are much hotter or ones that are much colder. It's basically when you're looking at stuff in space, so bigger temperature ranges. Here on Earth we use Fahrenheit and Celsius. Of course, Celsius everybody pretty much uses. There's only very few nations that use Fahrenheit. All of our surface maps are still in Fahrenheit, and all of our upper air data is in Celsius. What most people use. That Celsius is the actual standard unit. And you can convert back and forth. I would never ask you to convert because it's something you can look up on the internet. It's very easy to do as opposed to sitting down and actually calculating it out. But it's obviously possible to change from one unit to the next. And you can see how they compare along here. 0 degrees Celsius is 32 Fahrenheit, so that's the freezing point. And you can see how it compares to Kelvin as well. Here is the world's distribution of temperatures. These are all done in Celsius, and this is for January for the entire world. You can see it gets really cold, like dark purple, so minus 40, and colder in parts of Russia, this is January, so this means it's the winter time for the northern hemisphere versus the southern hemisphere getting their summertime. And you can tell where the land is. It's a lot hotter in central Australia, 30 degrees and above Celsius, parts of South America and parts of Africa. And again, those are all over land because land heats up faster into a higher temperature and cools down to a lower temperature at a faster rate as well. This is July, and you can see now it's northern hemisphere has their summertime. It's the winter for the southern hemisphere, and you can see again in the northern hemisphere where there's more land, then the temperatures are getting hotter, so 30 plus degrees Celsius here. Over in parts of North America and in Africa, where you get, in some places, 35 degrees Celsius and higher. Now, when you're looking at this, you can see that there's a change from January to July in the northern hemisphere. Looking at January, once again there was that minus 40 up in Russia, in the Asian continent, and then you can tell that there's a bigger swing in temperatures. So very much tighter distributions going on. If you look at the July, then in the northern hemisphere, again you've got that big change of warm in the January when it was of the cold. If you look in the southern hemisphere, there's not a lot of change going on. I mean, there's summertime, there was those isolated areas that had the really hot temperatures over land, but generally everything's pretty flatline. You don't get these huge meanders. And you can look back at it one more time where you've got these huge dips over in Asia, same thing as it gets over land for North America. And even when it's there summertime, there isn't a huge changes except for those one isolated spots over land. You look in over the July, again, you can see that ocean really stabilizes the temperatures overall in the southern hemisphere. A different way to look at it, still January, like average temperatures, but what's added in here is what they call the thermal equator. Now we know the equator is 0 degrees, it's a fixed point on the Earth. But if you look at what's called the thermal equator, you're looking at what the hottest part of the temperatures, how they move in different times of the year. So January, the thermal equator, where it's hotter, you can see when it gets over land, it will go a lot further south because this is again January, so southern hemisphere having their summer. When you get back over water, it's more level, and then it'll start to dip again over land, and then it'll head towards where there's more land in the southern hemisphere, which would be Australia. When you get to July, the northern hemisphere summertime, you can see it does the same thing. Here's the actual 0 degrees. And it goes a lot further to the north. So it heads up into parts of India and then down through Africa. And then it'll get closer to where it should be, closer to where the actual equator is. And then the hotter part will spike back up towards North America, and then it'll try to return back to its position for that time of the year. So that intense part heating of the Earth will adjust up and down because the fact that land heats up faster into a hotter temperature than water does. Now looking at it like this is the annual range of temperature, so you're taking obviously over the whole year. It just kind of gives you an idea overall of what things look like. and you can tell that there's more temperature changes over where there's major bodies of land. So parts of Asia, North America, and when you get down towards South America, I mean, it's not as large of a continent as the other two we just discussed, so you don't see as much of a change. Not a lot of information from looking at annual versus catching a monthly, like the January versus the July. Then you can really see how temperature is affected by water and land. Now, we can't go through all this without talking about the overall temperature for the Earth, what they call the global temperature. You can see the annual mean goes from 1880 all the way up to 2000, and then it has a 5-year mean. And generally speaking, it goes up and down. There's times when it goes up and there's times when it goes down. And over the last couple, actually many years, we've been noticing more of an incline upwards. But you can see individually it does adjust down because the Earth goes through all these changes throughout time. What's called the daily march of temperature just kind of gives you an idea of when you get excess amounts of solar radiation versus what they call deficit. So basically when the sun's up, you're getting a lot of extra heat. When the sun goes down, then it starts to remove some of that heat. The Earth will give back some of that heat, and that's caused by the rotation of the Earth because of getting day and night. So daytime you get a surplus, when it's nighttime you get a deficit, and overall the Earth tries to balance itself out by releasing some of the radiation, some of that heat it gets during the day. Your chapter 4 goes over some heating degree and cooling degree days. One of your investigation labs has it, but we don't do any of that. It's not very useful information. It's not stuff that you would see on a daily basis. You don't ever see forecasters talking about it because it really goes for more energy consumption. So if you're going to do anything in the energy business, then you would come across what they call heating degree days and cooling degree days. Basically, do you need to use your furnace and heat your house, or do you need to use your air conditioner and cool your house or building or facility, whatever the case is? So those what those temperatures deal with. And there's growing degree days that obviously helps you decide when you're going to plant. Another way to look at it is, and this is something we use, is wind chill index and the heat index. And what it does is it gives you a number to tell you what the temperature is like when you factor in the wind. Because when you factor in the wind, it feels a lot colder than it actually is. And this is one of the charts from the National Weather Service of what's actually used. And all you do is you find the temperature of the day and then the wind speed. So let's say the temperature is 15 degrees, the wind speed is 20, then it feels like -2 instead of 15, which is the actual number. So it doesn't really mean a whole lot, except for it places a number to us. So that way you're like, oh, the wind chill's -2. So I know that even though I saw 15, which is still a cold temperature, that -2 is really going to feel a lot colder to me. So I need to dress more appropriately. So it's a lot to do with more how you should dress. Heat index, kind of the same thing, where it factors in the moisture and it feels hotter than it actually is. That way you would know whether to, how to prepare for the day so you don't get heat exhaustion. So it's the same idea. You take the relative humidity in the percent form and the air temperature. So let's say it's 95 degrees out, but there's 70% relative humidity, which would be absolutely crazy, but it'd feel like 124 degrees, which would be awful. So heat index and wind chill are something we would use. And the heating degree days and the cooling degree days, not something you would necessarily use, especially in forecasting for the weather, for people to know what the weather is going to be like.